We're going to look at a couple of simple equations and one that isn't quite as simple. Our first equation is going to be h prime of t equals t squared, or dh dt equals t squared. This will be associated with the direction field that's going to look something like this, not particularly well drawn, and we'll have solution curves within the direction field, as we've seen before. Just to put this in context, we're not going to talk too much about this right now, but remember that this is a picture of the behavior of this equation. If we integrate both sides, we integrate h prime of t dt and t squared dt. On the left hand side, we're going to get h of t plus a constant. On the right hand side, we're going to get t cubed over 3 plus another constant. We put those two constants together and express them on the right hand side, and we have curves h of t equals t cubed over 3 plus c. Now, this curve is plausibly the beginning of a t cubed over 3 plus c curve, where c is whatever value h takes when this curve intercepts the vertical axis. Okay, so that's straightforward, and this second equation is also straightforward. Dx dt equals 3t. The direction field looks like this. We will note that both for this function and this function, the value of t is the only thing that indicates the slope, that's relevant to the slope. So that all the slopes for this value of t here along this vertical line are going to be the same, and along this vertical line all the values of t are identical, so that again the slopes are all going to be the same along this vertical line. This is easily integrated. We integrate both sides. If we integrate dx dt with respect to t and integrate 3t with respect to t, we get x of t over here plus a constant equals 3t squared over 2 plus a constant, and we'll let this constant absorb whatever this constant is. And we see that this is just a set of parabolas, and a family of parabolas will fit this direction field quite well. Again, fairly straightforward solution. Over here, we've got another equation, dx dt equals 3t plus x. We've seen cases like this, and we've had some explanation, but it won't hurt us to see again why this equation is harder to solve. In the first place, in contrast with the preceding example where the slopes were the same along vertical lines, because of course t remains the same and the slope depends only on t, in this case we have 3t plus x, so that along this vertical line on these three dots, the x values are getting larger and larger, which means that the slopes are going to increase. So we've got a slope here. Our next slope is going to be a little greater. Our next slope will be a little greater. Our next slope will be a little greater. And also, as we move to the right along horizontal lines, our values of t are increasing. If we move along a horizontal line, x stays the same, but t increases. That means our slopes are going to increase, so that as we move from here to here, the slope increases as it should. And as we move to the next point, the slope will increase even further. And our direction field might look something like this, where the slopes are increasing as we go up and increasing as we go across. Now, if we try to integrate both sides of this equation, we run into trouble. Of course, we can integrate dx dt with respect to t, and we're just going to get our x of t plus a constant. On the right hand side, we have to integrate also with respect to t, so we got to integrate 3t plus x with respect to t. Now, we can integrate 3t with respect to t. That's no problem at all. We get 3t squared over 2. But how do we integrate x with respect to t when x is itself some function of t and we don't know what that function is? Well, there's no way we can directly integrate that, so we just got to write this as the integral of x dt, and we can put our integration constant in at this point if we wish. but we have no way of finding an antiderivative of the x of t function, which is what we're trying to find. So again, in this situation, even though we can sketch perfectly sensible solution curves, we can't determine the function that corresponds to those solution curves. And as mentioned previously, we are going to develop techniques fairly soon that will allow us to solve for this function x, but we're not to that point yet.